Hello, everyone. I hope you're doing well today. I'm going to go ahead and get started here by opening up the page that we will be reviewing. So for starters, let's look at the syllabus for today. This week is going to be week 3, fractional distillation, experiment number 5. And what we're going to be doing is focusing on that as our subject. Make sure to go ahead and complete your quiz and to update your notebook. Please feel free to email me or contact me for a one-on-one Zoom meeting with regards to this experiment if you have any questions after watching the video. So I just wanted to show you this for this week. Next week will be week 4. We'll be performing simple distillation, and same as usual, make sure to try and get your quiz turned in by Friday for this. If you can't get it turned in for fractional distillation this week's quiz, please contact me via email. So let's go ahead and get started. Let's switch back. Okay, share screen, back to the module. We're going to look at that firstly. So, all right, looking at the module here this week, we will be, firstly, make sure we're going to go ahead and read through the fractional distillation experiment document from the lab manual and the PDF file. We'll be reviewing that here shortly. So on your own accord, please make sure to go ahead and watch these videos. Mainly today we'll be talking about fractional distillation right here. Watch part 1 and part 2 on these links within the module. And through the lab manual, there is not a gas chromatography section described there. So please make sure to watch this video created by Mackenzie and Grace. And finally, video 4 will be an additional informational guide towards fractional distillation if you need any more clarifications after I go through the lab manual with everyone. Since we won't be having our Zoom meeting, please make sure to go ahead and complete your lab notebook very clearly. If you need any assistance with it, of course, contact me as well. Same with the quiz, we already covered that. And then, so this would be the materials that we'd be utilizing in lab in order to perform the distillation, which we will discuss further within the lab manual. Finally, after you watch the video and you have watched the other videos right here that are linked above, you'll go ahead and complete your post-lab notebook and submit it here. In order to acquire your data, please make sure to click here. And then if your first name starts with A through M, click here for your gas chromatography spectra. If it starts with N through Z, go ahead and click here. And we will review this data after I go ahead and go through the lab manual with everyone. So let me switch now my screen over to the lab manual so we can go ahead and get started. All right, so firstly, today's lesson is over fractional distillation. What we're going to be doing is we're going to be combining 2 or more mixtures of different volatile compounds into a boiling apparatus in order to perform fractional distillation. As it says here, the same technique may also be used to separate volatile compounds from one another if their boiling points differ by at least 40 to 50 degrees Celsius. And if they do not, then the technique of fractional distillation is normally used to obtain each volatile compound. So if they have a very similar boiling point, it's good to go ahead and utilize fractional distillation so that way that you can slowly separate the 2 from each other. So coming down here, this explains out the exact partial vapor pressures and the equation utilized in order to calculate the mole fractions with regards to pressure. So as we look here, this relationship is expressed mathematically in equation 5.1, where Nx, the mole fraction of N, over Ny, the mole fraction of Y, is the ratio of mole fractions X and Y in the vapor phase. So the mole fraction of each component may be calculated from the equations. The mole fraction of X is equal to the pressure of X divided by the pressure of X plus pressure of Y, and the same for Y relative here. So as you can see here, this is the equation 5.1 right here. And if you're looking at the partial vapor pressures, Px and Py are determined by the composition of the liquid according to Raoult's law. That is not listed here, but I would still refer back to these equations here in order to calculate your mole fractions obtained. That we will be explaining this further as we go down into the chart so that you guys can look at the graph and understand better the mole fractions. And so right here, the relationship between temperature and the composition of liquid and vapor phase of ideal binary two-component solutions is illustrated in figure 5.1, which will be down here, so I'm going to zoom out just a little bit. Okay, so firstly, the lower curve is the liquid line, giving the boiling points of all mixtures of the two compounds. So when they say that right here, where they have it listed on this chart, the liquid line is this lower line right here. And then going forward, the upper curve, which is the vapor line, is calculated using Raoult's law and defines the composition of the vapor phase in equilibrium with the boiling liquid phase at the same temperature. So it may be a little confusing because as you can see, you have your liquid line here and your vapor line here, but we'll go ahead and go forward to understand further what they mean by that by using an example. So for example, a mixture whose composition is 58 mole percent benzene and 42% mole percent toluene, it will boil at 90 degrees Celsius at 760 torr, which is at ATM. 1 ATM is 760 torr, which is average pressure of like room pressure. I don't want to say room temperature because it's relative to the pressure, but standard ATM, 1 ATM is the standard pressure that we utilize in a given atmosphere. So if you look here, 58 mole percent benzene. So I went ahead and kind of like made a little bit of writing on here so you guys can understand this better. Down here, mole percent toluene is the top value, mole percent benzene is the bottom value. So if we look mole percent benzene right here, 58%. And then if you look right here, mole percent toluene is about 42%. And so what's happening here is that it comes up here, and this is at the liquid line. They're both liquids at here at point A. And what happens is that if you boil it, then it comes over here to point B, the vapor phase. And this is all at 90 degrees Celsius, right? So it's boiling here at point A, and it comes over here to point B, and then it will go back into liquid phase once it distills off. So if we read here, we would understand the composition of the vapor in equilibrium with the solution when it first starts to boil can be determined by drawing a horizontal line from the liquid to vapor line. So right here, point A is where we started at, 58% benzene, 42% toluene, boiling at point A, 90 degrees Celsius. Then it will come over here and vaporize to point B. And if we look at that, then we would say, wait, well, it's not at 58% benzene and 42% toluene anymore. It's actually moved over here to where it is a composition of about 78% benzene and 22% toluene. So what that means is that since benzene is more volatile than toluene in this situation, obviously you can see that 58% and 42 versus 42%, that it would come over here, and when it's up in the still head, it would be a composition of 78% benzene and 22% toluene at the top in the vapor phase. And so this is a key point for any means that any given temperature as the vapor phase is richer in the more volatile compound than it is in the boiling liquid, which the vapor is in equilibrium. So this is the exact idea of fractional distillation, because what happens is that you're separating the more volatile compound, in this case benzene, it's more volatile than toluene. And the idea is to boil off the benzene, and then you would have it distilled off into another container, and then you'd be left with the toluene. So as I wrote here, boiling off the benzene, leaving toluene. So this diagram is to be used, and you would keep going forward if you were to continue to boil, and it would come back down. You boil it again here at point C, going over to point D. Then you would be going back down, and then you would, move over here to like the 90% benzene, 10% toluene, and you would continue to go until you would have, one whole portion of benzene distilled off over here, and then you would have pure toluene left in your boiling flask, because the toluene wouldn't boil over since it is less volatile. You'd be controlling the temperature specifically here, utilizing that 90 degrees Celsius in order to get all of your benzene over and to keep your toluene in your starting flask. So it kind of goes back over again to what happens here, that starting at the 42% toluene and the 58% benzene would come over. In the boiling point, the vapor form initially contains 82% benzene and 18% toluene, because it comes over here and that's the vapor. It is condensed mostly of benzene and of a slight small amount of toluene. The first vapor is condensed and it also has this composition, thus it would be much richer in benzene than the original liquid mixture. Afterwards, then the liquid remaining in the still pot is a smaller mole percent of benzene and greater mole percent of toluene, because the benzene, more benzene than toluene was removed by vaporization, because benzene is more volatile. So that's the reason that it's boiling off more readily than toluene is. So the boiling point of the liquid remaining in the distilling flask will rise as a result. So what happens is that since the boiling point of the liquid remaining in the distilling flask is dependent on what is left in the distilling flask, so what would be left would be mainly more toluene, since you would be pulling more benzene over, and the higher molar ratio, the molar fraction of toluene to benzene is going to increase. And so that would mean that your boiling point would therefore increase, because you'd be left with less benzene and more toluene. As the distillation continues, the boiling point of the mixture will steadily increase until it approaches or reaches the boiling point of pure toluene. So if you look here, the boiling point of pure toluene, 100% toluene, is all the way up here, whereas the boiling point of benzene is closer down here to about 80. And if I were to look up the two of them really quickly, I'll just go ahead and Google it for you all, so that way I can explain to you. So the boiling point of toluene is 110.6 degrees Celsius, and the boiling point of benzene, I think it's near 80. Yeah, it's 80.1 degrees Celsius. So benzene is at 80.1 and toluene is 110. So as you continue to boil your mixture, then slowly your original mixture will require more heat, because what's happening is benzene at the lower boiling point is coming off and distilling down off of your column, and then you're left with more and more toluene. So slowly the boiling point increases. So as you see here, since you've already gone forward and pulled your benzene off, if you have more mole now of toluene, instead of 48%, let's just say hypothetically it's up to like 62% now. Well, this isn't a very descriptive graph of the temperature, but you would assume here, 62% coming up here, it would be much higher. It'd be about 100. And then, of course, if you're at 100% mole percent toluene, they would go all the way up to 110 degrees Celsius required for it to boil off only toluene. So going forward, we talked about that. So this continues to explain out, the continuation of boiling and boiling over more and more of the compound. So in theory, the process could be repeated again and again to give a very small amount of pure benzene. And that's the main concept here, is to continually boil off the more volatile substance and to eventually be left with the pure substance in one flask, and then a composition of the other flask. And if you wanted to actually isolate benzene, then you'd have to continue to take what you've boiled off that has a mixture of benzene and toluene, and then to continually do that until you only had benzene. In this system, if you had your mixture, you'd be left with toluene in the main boiling flask, and it would just continue to rid of the benzene. So this goes forward just to explain further the idea of homogeneous solutions of volatile organic compounds. So the most important portion coming over to here is that the minimum boiling mixture composition Z in figure 5.2 may be considered as though it is a third component of the binary mixture. So in this system, we are actually talking about if you were to have two volatile liquids that have a certain boiling point that is exactly equivalent. So the issue in this situation is that it has a constant boiling point because the vapor in equilibrium with the liquid has composition identical to that of the liquid itself. The mixture was called the minimum boiling azeotrope. So this is important right here, is the azeotrope as a statement, because whenever something is azeotropic, then if you look right here, they're talking about the minimum boiling mixture composition in Z in figure 5.2. So here, if at a given temperature and you're given a molar ratio of mole A, let's just say that's about 30% mole A and about 70% mole B, then here at point Z, unfortunately what happens is If you decide to boil it and it's that 30% to 70%, it's an azeotrope at that point, meaning that both will boil equivalently at that point. So at no point can you actually separate the two if you have the 30 to 70%. So if you were boiling it at that given temperature, and it doesn't have it listed here, so it's not a very good example, but if you have it boiling at that given temperature and you have 30% of mole fraction A and then 70% of mole B, then they both would boil over and distill off. So unfortunately, you would not be able to actually purify it at that given temperature. So as I say here, fractional distillation of such mixtures will not yield both of the components in pure form. Rather, only the azeotropic mixture and the component present in excess of the azeotropic composition will be produced from the fractionation. And as an example, pure ethanol cannot be obtained by fractional distillation of aqueous solutions containing less than 95.57% ethanol, because it's combining with water and having this similar effect, where instead of it continuously going down and then down and down like we had up here with toluene and benzene, it goes from point A to point B, then down to C to D, down to E to F, and then eventually you would have one of toluene and one of benzene. In the system, there, as you boil down and you come forward and you keep going and you keep going, it comes over here to Y, goes down, eventually you get down here to Z. Well, what happens? The issue is that it doesn't continue to crawl down. Instead, it actually begins to crawl upwards, and you end up making a more impure solution, an azeotropic mixture. So it is a useful technique for removing water from organic solutions. For example, toluene and water form an azeotrope having a composition of 86.5% toluene and 13.5% water. And so distillation of a mixture of these two effectively removes water from mixture. So it is good for removing water from a mixture in the sense of an azeotropic distillation with toluene and water, but certain things such as ethanol have issues with going forward and actually boiling above and performing fractional distillation that would allow you to separate the two. So going forward into understanding more about the fractional distillation, there are many types of fractional distillation columns. And the most important part that I wanted to take from this here is that if the lower part of the distilling column is maintained at a higher temperature than the upper part of the column, the condensate will be partially revaporized as it flows down the column. So what happens is that if you think about it, that the lower part of the distilling column is at a higher temperature because it's closer to the heat source, and then the vapors heat up to the top, and then what happens is that as it goes up, the temperature is cooler at the top, and then it will condensate at the top since it's cooler, coming out of the vapor phase back to liquid and coming back down, and then it continues in the cycle. Since you have a higher temperature at the bottom, heating it up, and then it comes back up into vapor, and then it condenses as a liquid and comes back down. So the uncondensed vapor together with that produced by revaporization of the condensate in the column rises higher and higher in the column and undergoes a repeated series of condensations and evaporizations. So this continuously turns into vapor, condenses, comes back into liquid phase, and comes back down. So going forward, this repetitive process is equivalent to performing a number of simple distillations within the column, with the vapor phase produced in each step becoming increasingly richer in the more volatile component. So what happens is in that same situation with the toluene and benzene, the benzene is more volatile. So what happens is that the vapor phase continuously takes more and more of the benzene out, and the toluene ends up actually condensing back down because it's coming back at that lower temperature and falling back down easier since it's less volatile than the benzene is, and the benzene is more volatile. So it is more likely to go up into the vapor and stay in the vapor and then actually come off of the column down into your receiving flask instead of going and condensing and vaporizing, sorry, re-vaporizing back down into the boiling vessel. So going forward, each step along the path of A, B, C, D, E, F, figure 5.1, we're reverting back to the first original image we looked at is a single ideal distillation. So that is just the concept of what happens when we're performing the fractional distillation. And so one type of fractional distillation column, the bubble plate column, is designed to help effect for each one step for each plate to contain. This led to the description of the efficiency of any fractional distillation columns in terms of equivalency of an idea of theoretical plates. Another index of separating efficiency of the fractional distillation column is the HETP, which stands for high equivalent to a theoretical plate. And it's the vertical length of the column that is necessary to obtain a separation efficiency of one theoretical plate. And so to give an example to kind of clarify what they mean by these theoretical plates is that a column of 60 centimeters long, so 60 centimeters tall, with an efficiency of 30 plates has an HETP value of 2 centimeters. Such column would be better for research purposes than a 60 plate column that is 300 centimeters long, which would have an HETP of 5 centimeters because of the small liquid capacity and holdup of the shorter column. So when they're talking about this here in reference to holdup, the word holdup refers to the condensate that remains in a column during and after distillation. So they're saying this would be better for research purposes than a 60 plate column, which is like a lot taller and longer column because of the small liquid capacity and holdup of the shorter. So the shorter column, better in its research purposes, has a HTP value, which is a smaller value for this smaller kind of research. If we're not performing very large, massive cauldrons of boiling where we would need the longer columns and the better separation. So in the sense that we're using a smaller column and an HETP value of 2 centimeters, it would be helpful to have a smaller radius, a smaller HETP value for separation, for the sake of, since we have such a smaller amounts, you want smaller separation. And when they talk about the holdup refers to the condensate that remains in the column during and after distillation. So the holdup is that in-between stage when it's boiling from the flask up into the column. The holdup is the liquid that is up within the column, and it can be like the actual liquid at the bottom, more near the still pot, and also the vapor and liquid that is condensating at the top at the still head down back into the column. When small amounts of material are to be distilled, a column must be chosen that has an efficiency HETP adequate for the desired separation and also low to moderate holdup. So you don't want too high of holdup, because if you just have a ton of condensate building up in your column, then your separation is not as efficient, because the idea is to have the less volatile substance that's in there to be able to condensate back down and not get just like a trap of large amount of liquid in your column at the bottom, because you want it to actually flow back down into the flask that you are boiling into, or that you're boiling from. You want the less volatile to drop back in there in order to continue the cycle of boiling off the more volatile, in the case of benzene, and so that the benzene actually goes into vapor and comes off. But if the benzene is blocked by that toluene sitting there as a large, clump of water right above your still pot, but stuck in the column, then the benzene can't efficiently come out and actually boil out off over into your receiving flask. So going forward with that idea, after all of the more volatile component is distilled, benzene is more volatile in that case. The less volatile one remains in the column and the still pot, toluene. So the toluene would stay in the column and continue that cycle where it would come back down, be hot enough to boil, but then it comes back to the still head, and then it's too cool, so the vapor actually turns right back into liquid, and then it condenses back down. So it's like this constant cycle of the less volatile substance, the toluene, coming back down and condensing, and the more volatile substance, benzene, going up into the vapor phase and eventually going down off the column over into the receiving flask. So that the important requirements for a successful fractional distillation are separated here into 4 different things: A, B, C, and D. Portion A is the desired contact between liquid and vapor phases. Can be achieved by filling the column with an inert material that has a large surface area in order to separate more of the volatile from the more volatile from the less volatile substance, in that case, toluene versus benzene. Examples of suitable packing is glass, ceramic, or metal pieces. And so what they mentioned here, I actually pulled up a picture to show everybody the difference between the VigorX column, which is useful for small scale distillations of liquid where low holdup is of paramount importance, and also the Hempel column. So the VigorX column has the advantage of holdup of less than 1 milliliter as compared to 2 to 3 milliliters for a Hempel column filled with rushing rings, which are just little glass rings. And so let me switch my screen over here for a second. Over to, here we go. All right, so this one on the left is the VigorX column. As you can see here, it actually has its own indentations within the column itself instead of being like the Hempel. The two on the right you see here are Hempel columns. You can run water through them in order to disperse the heat throughout it. And as you see in the Hempel, it is filled with steel wool or commonly glass beads or rushing rings. And this allows the separation of the volatile from the more volatile from less volatile components within your boiling mixture. However, in the VigorX, we don't have to utilize the steel wool or glass beads because the surface area is separated more by the separations within the column itself that are naturally built in. So it creates more of a surface area to be able to condense onto, and more area also for the more volatile to vaporize up into the top and separate off. And I'll show you further the images of the full setup and apparatus, because I keep putting my hand up and going like this, and everyone hasn't seen yet what the image is. But once you see it, you'll see that it boils up and then it condenses off over down into a separate receiving flask. So now you see on the left the VigorX once again, and on the right the Hempel fractionating columns. So let me go back over to the lab manual. So yes, so VigorX column has the advantage of holdup of less than 1 milliliter as compared to with 2 to 3 milliliters for a Hempel column filled with the rings, beads, or the steel wool. So if we were to be performing it, we would like to use the VigorX column for small scale distillations where low holdup is very important, because the more holdup, as we discussed earlier, will disrupt the separation of your less volatile and your more volatile substance that you are boiling. However, if we have a larger quantity that we are trying to separate, then we could go ahead and go forward with the Hempel column and either use glass wool, glass, ceramic, or metal pieces in order to increase the surface area and allow the separation of the volatile from the non-volatile compounds. Or more to say, the more volatile and the less volatile, because they both are volatile, but as you saw, benzene has the boiling point of 80 and toluene has the boiling point of 110. So the second thing is the temperature gradient. So this refers to the difference in temperature between the top and bottom of the column. So the top of the column, if you think about it, the bottom of the column is closer to the still pot, which is boiling. So it's always going to be hotter. And then the temperature gradient rises as you go further up the column. There's less heat at the top. So the temperature gradient is very important here, because ideally the temperature at the bottom of the column should be approximately equal to the boiling temperature of the solution in the still pot. And it should decrease continually. So as you go up the column, as the liquids travel up the column, the vapors travel up the column, then eventually it gets cooler at the top. And at a certain point, it should be cool enough to where that your more volatile compounds can cool down and turn into liquid condensate, and then come down off of your column into a receiving flask. So it should decrease continually in the column until it reaches the boiling point of the more volatile component at the head. So the more volatile component, once it comes out of, let's just say like the 80, or in that instance, the 90 degrees Celsius for the compound mixture, once it comes to the top and it came from being at 90, let's just say it drops down to 85 degrees Celsius and it's almost there, and then it finally hits 80 once it's at the very top. And then 80 is the boiling point of benzene. So once it hits there, it would condensate back into liquid form of benzene and then distill off into your receiving flask. So the significance of the temperature gradient is seen in figure 5.1, referring back to the image that we saw up there, where the boiling temperature of the distillate decreases with each succeeding step. So that just shows that up here, the boiling point is decreasing for toluene. The boiling point is decreasing for benzene, because as you boil it in this mixture of toluene and benzene, it requires more energy to to boil because of the toluene within the mixture, but as you keep going forward, the benzenes requiring less heat to boil because there is less of it within the solution. So coming back here, the necessary temperature gradient for still pot, still head, still pot at the bottom, still head is at the top, as you can think of like the pot is at the bottom and the head is at like the top of a person. So the still head is at the very top where it's condensating. The still pot is the bottom where it's boiling your mixture. Be established automatically by condensing the vapors if the rate of distillation is properly adjusted. And then we kind of go back forward into the glass wool and other substances used in order to separate and create a larger surface area. The rate must be then increased, but it must be kept below the point where the column is flooded. And the flooded column, like I was saying, is a column or plug of liquid that may be observed within the distillation column, often at the joint between it and the still pot. And I'll show you an image of that going forward. The main idea is that you don't want the column to get flooded where there's a bunch of condensate of your less volatile substance within the column at the very bottom, and not allowing the vapors to rise through and to condensate at the top and separate off what your more volatile substances that you're trying to obtain. So you want to just make sure that the temperature gradient is good enough to where that, you know, you get your separation of your more volatile, but also not too severe to where this still pot is being extremely heated and that it ends up flooding the column there with your returning condensate of your less volatile substance. The proper operation of a fractional distillation requires careful control of the heat. Yeah, so you don't want to be heating it too hot and too fast, because then you'll just get boiling and it'll start refluxing. And then you'll get all of this flooding in your column where you just have a large amount of liquid of your less volatile component that's actually blocking you from being able to distill off your more volatile component. So then you would have to lower the heat a little bit more and just go a little slower. It's all about slow and steady wins the race with regards to fractional distillation. So coming down, the ratio of amount of condensate returning to the still pot and the amount of vapor removed as a distillate per unit time is defined as a reflux ratio. So as an example, a ratio of 10:1 means that 10 drops of condensate return to the still pot for each drop of distillate that is obtained. So in this theoretical idea, you know, 10 drops of condensate comes out of your still pot boiling up, 10 drops come to the top of your still head, 1 drop of the volatile substance, more volatile substance comes off and condenses, or sorry, it comes off and distills, and then you know, the rest of this condensate condenses back down, and that would be equivalent to a 10:1 reflux ratio. In general, the higher the reflux ratio, the more efficient of the fractional distillation. So that they're saying that if you have a higher ratio, you know, like 20:1, every 20 drops, you get 1 drop of distillate obtained. That means that it's more efficient fractional distillation. Correct column length is difficult to determine. So usually they say a longer column or different type of column or column packing must be selected if you're having improper distillation. So a lot of it is not a tried and true statement for each type of substance. Some of them will require shorter columns, some of them require longer columns, or, you know, switching over to our other Hempel column or the Vigor X column, depending on the substances that we're separating. And finally, the difference in boiling points between the two pure components of mixture should be no less than 20 to 30 degrees Celsius. Otherwise, we'd be utilizing simple distillation. So we just want to make sure that the difference in boiling points between the two components should be no less than 20 to 30 degrees Celsius. And so finally, we want to understand that under such conditions, 2 different temperature plateaus will be observed in the fractional distillation of a typical binary mixture, and that the head temperature should first rise to the normal boiling point of the more volatile component and remain there until that component is completely removed. So that idea that the more volatile component is rising up once again, and then it's going to remain there and then slowly distill over, and the less volatile is going to condense back down into liquid form and then return back to the still pot, and the continuous cycle will keep going until assumed all of the more volatile compound has come out and distilled off over into the collection receiving flask. So here are many safety components that everyone needs to make sure to have written within their lab notebook, because this can be a dangerous procedure, especially utilizing different forms of volatile substances that are flammable. So in this scenario, we'll be performing a fractional distillation to isolate 2-butanone and 2-pentanones. And going forward, if we look up here on Google really quick, I'll see 2-butanone boiling point. 2-butanone's boiling point is 79 degrees Celsius. 2-pentanone boiling point is 101 degrees Celsius. So we're looking at a difference between 80 degrees, about 80 degrees Celsius for the butanone and 101 degrees Celsius for the pentanone. So as you would see that the butanone, since it has 80 degrees Celsius as a boiling point, that would be more volatile than pentanone at 101 degrees Celsius. So make sure to read through the full procedure and to follow these instructions when you're writing them, as if that you are going to be performing this form of distillation within a lab setting. And so in here, we would go ahead and look at the scenario given here. If you were to be setting this up, you would have 2 support stands. One support stand would be holding here your supporting ring that holds your heating mantle, and the heating mantle would be electric in this scenario. We wouldn't want to use something like a Bunsen burner, especially if we're using flammable solvents, because if something were to leak out, you could cause a flame and possibly an explosion due to the volatile substances we are dealing with. They are all flammable, especially 2-butanone and 2-pentanone. So you put boiling chips inside of this, so that way that it allows it to boil once you raise the heat. The pot is the still pot that the component mixtures would be placed into. Then a fractionating column is placed on top of this and sealed with a little bit of grease in there, just to make sure that you get a good seal and that the boiling, the condensing goes up into the column. As you can see here, if I zoom in just a little bit, you would have some sort of either glass beads or glass wool in order to increase the surface area and increase your separation of your distillates. This here, as you see the still head or the distilling head, is where the condensation will occur. The thermometer is kept up here, so that way that you can see what the temperature is up here at the distilling head, at the still head. And the still pot should be, relatively close to what the heating mantle's temperature is. And so when we look up here at the temperature, we can tell exactly how hot it is up here relative to the temperature down here at the heating mantle. And so as the more volatile substance comes up here in the vapor phase, it will end up distilling off. And this is the part right here where I was talking about it goes up and then distills off, because you will have a separate reflux condenser where the water goes in, comes up, and then the water comes out. And the water comes in right here in the bottom, so that way that the cool water comes down and up and takes the heat effectively out of the system. The cool water comes in, and then as it's coming over here, it's cooling down that condensate that's coming down the tube, coming down the column, and the water is surrounding that column, cooling it down. So as the more volatile substance comes down the column, it is condensing faster and is cooling down with the water that is traveling through this reflux condenser. And then this is just a clamp holding together everything, making sure that you have your support stands for everything to be on appropriately. And then this is your receiver. It could be a flask. In this situation, it's a graduated cylinder. This adapter just allows it to condense downwards instead of just going straight out of the condenser. The adapter allows it to actually drop vertically down into a receiving flask, or in this case, a graduated cylinder. So this is a great image to show exactly how a fractionating distillation occurs. Make sure to read through everything here with regards to how the procedure will be done. And then finally, come down here, complete your post-lab questions, and feel free to ask me any questions regarding these. If you need any assistance or understanding, I can always point you in the right direction and also show you some alternate resources if you need to further understand this better. Okay, now what I'm going to do is go ahead and switch my share over onto the next material. Let's see. Come here. Okay, so students A through M, you'll be utilizing this data here, and you will be running, it would be as if you had separated your components and you ran a GC, gas chromatography, on the components, and you would see, and you would have this sample A you've run 2-butanone separate from 2-pentanone, sample B run, and then a sample C run. And if you are from section, or sorry, if your first name starts with N to Z, then you would go forward right here and utilize the data for fraction A, fraction B, and fraction C. And so as you can see, even just to assist you guys just slightly by looking at the data, fraction A, mostly butanone, less pentanone, fraction B, almost equivalent, fraction C, mostly pentanone. And then over here, if we look at the A through M data, mostly butanone, a little bit of pentanone. Then we're starting to switch over and get a little bit less of the butanone, more of the pentanone. And then finally, a very small amount of butanone and more of the pentanone. And so that kind of refers back to when we were talking about the separations. At first, you'll get a large quantity of the more volatile substance coming over, and the less volatile substance distilling or condensing back down into your still pot. And as you go forward and you slowly keep increasing the temperature, well, what happens is less of the more volatile substances present to distill over. And as you keep increasing the temperature, you eventually will get to the next boiling point of the less volatile substance in the mixture, in that case, the 2-pentanone. Another key point of organic is to understand boiling points, as that whenever you look at something, butanone versus pentanone, you would know that butane is a 4-carbon, pentane is 5-carbon. And as you increase the amount of carbons, that increases the boiling point. So that is the reason that 2-butanone has a boiling point of 80 degrees Celsius and 2-pentanone has a boiling point of 110 degrees Celsius. So let me stop share here for a moment. And I have go ahead and gone through all of the information there with the lab manual and shown everyone the images of columns. Let me double check and see if I have anything left here to share today. So it looks like that I believe we have gone through everything that we needed to see. Go ahead and share this again. Please make sure to complete your quiz by the end of the week. If you have any issues with regards to power outages during this current weather disaster that we are having, please feel free to contact me and we will work with you so that way that you don't lose points from not having power at your house to be able to complete your due data, your due quiz or your lab notebook. Please make sure to contact me if you have any further questions or if there's any situations going on with regards to your power. And that will be it for today. Make sure to utilize the data down here and then to complete your data in a separate notebook. As well, make sure, this is the last point I should also touch on, is this data right here. Download the data. Oh, also let me know if your name is not on this list. This data here will be for your fractional distillation, and then you'll have to calculate your percent recoveries of each. So if you have any further questions, please feel free to contact me either via email or we can have a one-on-one Zoom meeting. Otherwise, that will be it for today, and I hope you have a great day.